So in this video, we're going to go ahead and talk about the Update International 10-point plot, which is a type of modal resonant analysis that you can do in the DT6 software. So if we toggle over to modules, we'll find the 10-point plot right here with this kind of the shape to kind of signify resonant curves. So we'll go ahead and click that. And the first thing it'll pop up with is how long do you want each reading to be. So most of the time you can just hit the default of 3 seconds. If you do it longer, you'll get higher frequency resolution later, but it doesn't really matter, to be honest. So if we hit OK, then we get this screen. This is the main acquisition screen for the 10-point plot. So right here we have two tabs just to kind of toggle what the background image is, just so you can kind of remember what it is you're trying to look at, but it's purely for aesthetic point. But here we can see how it's set up. So although it's called a 10-point plot, in reality you always take 11 points because it's 10 differences, so you have to have 11 measurements. But basically the way it works is you leave the blue sensor in some location and leave it fixed there throughout the entire setup process, and then all you do is we'll just go ahead and click and we can move the green sensor to wherever we want it. So if we were to try and take readings, we would just put it here, and then we would tell it which orientation our sensors are in. So for instance, most of the 10-point plots I do here in the office, the setup is on a long horizontal platform. So I put the sensors in the vertical position, which means that the magnet is, pointed towards the ground as opposed to being towards a horizontal shaft like it normally would be. But if you have it towards in the normal orientation, you'd go ahead and switch it to normal. But most of the tests we do here are vertical, so it just defaults to vertical. But you go ahead and change that, and then you just leave the blue sensor where it is, and then you just put the green sensor in this location or wherever you want. You can do any of these in any order just by clicking, and once the green arrow moves there, you're telling the software you're going to take this measurement. And then you just hit acquire, and once it's done taking that measurement, then you just click to the next one and then take it, and so on and so forth. And you don't technically have to take every measurement, but it's best if you can. The other thing I'll mention, that it's best if each of these measurement points are physically spaced out as equal as possible. So if you maybe take a measurement every 6 inches, that would be good. And you kind of want to take it over the whole length of whatever it is you're looking at. So if you're looking at like one specific unit, for instance, you would want to take it from as far to the left as possible to as far to the right as possible or something. But in this case, I'm just going to go ahead and import data just because it's a little bit easier, so that I don't take all this time to take the data. So if we just import, I'll just go ahead and click this one. Go ahead and open that, and you can see that as you take readings, each of these lights would turn green. So you basically would just hit acquire, and then once the little dot turns green, you have that reading, and then you can just move forward and whatever. So once you have all this data, then you can go up here to the tab that's labeled 10-point plot, and you go ahead and click that, and that's where we can actually start seeing the analysis. So we'll go ahead and hit choose new frequency, because the software will work to analyze the resonant at any frequency. So the first thing it'll ask is, which channel do you want to see the waterfall plot for? So the way you choose the frequency is you choose a waterfall plot. So in this case, I have a feeling the resonance is in the vertical. So I'll go ahead and click vertical, and it'll just show me a waterfall plot of the vertical. So in this case, you can see frequency increases this way. Then this way are each of those readings in order. And then the height is, the amplitude. And so the height and the amplitude don't really matter at all for this, so that's why they're not really listed. And if you ever have the views get kind of messed up, you can click here, default view, or we can look at along the frequency side or the plot side. But in this case, I'm going to go ahead and go to default, and then down here we have some ranges. So this changes where the range of frequencies we get to see is. And so in this case, I'm going to go ahead and zoom in down low, and I'm going to try and look for some sort of range of amplitudes that doesn't seem to be even the whole way through. And one of the ways we can kind of see which colors are changing is over here we have some amplitude threshold levels that will change the color, and if we switch this black to levels, it'll change the color of peaks that are portions of the frequency that are above that amplitude threshold. So in this case, if I lower yellow to like 0.1 and lower orange to like 0.2 and put red at like 0.3, we can see that this frequency right here, if we move this cursor, and then to move it, you just click and drag it and then let it drop on the peak. You can see that at that frequency, and let's go ahead and sweep up a little bit. There we go. We can see that the amplitude of this guy actually goes up to here and then kind of comes back down, right? And in this case, the one I really want to look at is, from my own experience, if we zoom back out a little bit, it's this guy right here. So again, you can look at any frequency you want, or sorry, excuse me, this one. So you could analyze the resonant at any frequency, but in this case, I know for a fact, just from experience, this is the one I care about. So you can kind of see here, if we zoom in a little bit closer, these amplitudes go up and then down and then up, and that what you're looking for when you're trying to do this sort of resonant 10-point plot analysis is to look for some amplitudes that go up and down, because that means that they're not uniform in size along the length of whatever device or unit or pipe you're testing or something. So then over here you can see that there's a frequency view, which basically shows you all of the amplitudes at that frequency. So right here we have 42 hertz chosen. So this shows all of the amplitudes of each of those measurements at 42 hertz. And then we can toggle the channel, which will show for the channel we have selected going this way. If we look at it this way, you see I have the fourth one right now kind of highlighted by these kind of dark gray boxes. You see the fourth one's highlighted. This shows the FFT of that. But the frequency view is arguably more useful in this case. So here we can see, yep, okay, we got an amplitude that goes up and down. And when you're looking for possible resonances, you're looking for things that seem to follow like clear sinusoidal shapes, and where at some point it has an amplitude close to zero and somewhere else it has an amplitude really far away. That's a pretty good indication there might be a resonant going on, because in a resonant there's always some spot that has zero amplitude because of the way it works. And so here, now that we've chosen this as what we think is our problem, we can just go ahead and hit return, and it'll automatically pop in that data here. And we have two tabs here. We have vibration data, which will just show us for that frequency we just chose. It'll show us a vertical plot here. So this is the amplitudes. And we can toggle on whether or not we want to see a negative version of those amplitudes, because that can sometimes help you get an understanding of what the curve kind of looks like as the shaft resonates, how it moves up and down. So you can kind of flip a negative, and here you can kind of see that it would be in one half of the curve at one point, and then here it would shift to this bottom half. So the resonant is kind of going back and forth like this. So this would look kind of like it's a 2-point resonance. And it looks like over here it didn't come back down to zero because I didn't quite take as many. It looks like the resonant of this part that I'm looking at is actually further than just where my motor ended. So it's actually probably the base that it's sitting on. But we can click right here on the bottom curve where it shows the phase. We can click and drag this yellow cursor, and here we can see a phase kind of plot in terms of a circular phase plot to see how the phase changes as we go along the points. So here, I don't know if you can see, but we're kind of in the top right region all the way here, and then right as we pass this 7-8 we flip to the other side. So that's a pretty good indication there might be a resonant going on, especially because again we have close to zero amplitude here, close to zero amplitude here, and close to a high amplitude here, and probably another high amplitude over here. This really points towards a resonant. And so in this case what we would do is, if we were trying to mitigate this, if we decided that this resonant was a problem, what we would do is here where it's close to zero amplitude, these are called nodes, and here where it's at a high amplitude, these are called antinodes. And if we were trying to mitigate this, we would want to put a brace or a mass or something right here at the antinode, because if we put it at one of the nodes, its vibration is already effectively zero, so either stiffening it or adding mass won't actually do anything. It's one of the common issues that people have when they try and mitigate resonance is they put their weight or their stiffness clamp or their their piston or whatever in the nodes, and that's actually the wrong spot. They have to put it here. So that's the first thing to note. And here we can toggle to see what the other channels look like for this given frequency. So here in the horizontal, we can see that it basically, we have high amplitude here, then it goes down to 0, and then it goes low. In this case, what it kind of looks like, and I'll show you this on the other screen. So this looks like it could potentially be a resonant, just because again we have 0 amplitude and then a high and a high. But resonances have to go back down to 0 at some point because of the physical limitations of the system. The ends don't move in a resonant scenario, at least most of the time. I can only think of one example where that wouldn't be the case, and that's in a cantilevered beam. But for most purposes, the ends have to go back to 0. So right off the bat, this part looks like it might be resonant, but then the ends don't go to 0, so that could be an indication that it's not actually a resonant. And then in the axial, we see basically, if we get rid of the negative values, we see that it doesn't really go back to 0 anywhere. So this one is probably not a resonance of any kind. And again, we see no noticeable phase change, and in a resonant there should be a phase change. But I personally like to use the deflection shape animation where it'll actually animate out the shafts. So if we go ahead and do this, we can actually see how that shaft is moving. So it'll combine both the amplitude and the phase relationships to show how the shaft is moving at this frequency. So here in the vertical, we can clearly see it's not moving here. It's not really moving here, but it's moving a lot right here and a lot over here. So this looks a lot like a resonant. And then over here, we can change how fast it kind of plays this graph. So I think right here is kind of a good spot. So this looks a lot like a resonant, and in this case that frequency I chose was 42 hertz, which is actually the 3 times multiple of what this machine was running at. And it makes sense because the machine has a 3-jaw coupling, so the 3 times vibration is going to be the significant one because of the 3-jaw. And when I was tuning the speed of the variable drive, I could hear it get louder at this frequency, so I knew something at this running speed of the shaft was resonating, and it turns out it's this 3 times at 42 hertz. So that's why I wouldn't normally see it when I was at my full running speed of 30 hertz, but when I was put at a fraction of that speed, then we could actually see the vibration get louder, both physically and audioly, and this frequency is the reason why. And so here we can clearly see this shows a resonant curve, and if we were to try and mitigate it, if we decided it was a problem, we would either put a clamp right here between where we put our 4th measurement and our 5th measurement, or we would put some additional weight here or something, and that would hopefully bring this whole vibration down. If we go ahead and look at the horizontal, what we see is basically, I don't know, it's a little hard to tell here. So the unusual thing is this 3rd location, this 5th location seem to be leading their side, which is probably just a slight noise issue, to be completely honest. But the main thing to take away is it looks like this end is always up when this end is always down, and vice versa. So the net vibration is basically this way and then this way. So this is your characteristic misalignment case where on one side of the coupling it's going in one direction, and on the other side of the coupling it's going the other direction. And this 5th location turns out to be actually where my coupling is. I measured this along the base of the unit. So this horizontal doesn't show any sort of sign of being resonant. It just shows that it's likely just a misalignment scenario, in which case there's no resonant problem here. But the vertical for sure shows, especially if you think about it this way, the 5th location is where our coupling is. So here there's almost no vibration at the coupling, which kind of makes sense. But then we go to the vertical and there's huge vibration. So this looks like a resonant curve, whereas this just looks like it's showing a misalignment type vibration. And then if we look at the axial, we see that basically every amplitude is on the same side of the curve at the same time. So this doesn't really show any sign of being resonating, especially because there's not a single point that's ever staying at 0, which you have to have in a resonance. So I think it's relatively easy in the 10-point plot to get a rough understanding of what the resonances are in the machine. And then if, for instance, we didn't find any resonant at this frequency, we could just hit choose new frequency and go through the same steps from before and analyze it at a different frequency. And that way you can actually use the DT6 to measure the resonant potential at any given frequency and find out exactly where they are. If you have any questions, feel free to contact us at 303-986-6761 or 1-800-530-4215, and we'd be more than happy to answer your questions. Thanks, and I hope you have a good rest of your day.